Hello, class. So this is going to be our first lecture for this week. I'm going to go over projectile motion. I'm going to start off in one dimension and then go to two dimensions. And then we'll cover vectors. And then we'll come back to projectile motion later. Projectile motion is a real important type of motion, and you see that a lot. It's one that's analyzed by Newtonian mechanics in this class quite a bit. And at least several of you brought it up in the discussion posts, so that's great. It's really great to think about this type of motion because we see it all the time. So I'm going to start this problem by doing a classic problem. This is close to one in your book, but not exactly. I'm going to start off with a guy on a building. I'm going to do the building in black. And then draw the ground. And so in your book, this is a cliff with that keeps going without the ground. So this is a little bit different numbers too. Okay, so then I'm going to draw a guy. Oh, draw a guy here. Okay, and he's going to drop a ball. Well, he's actually going to throw the ball up in the air, and then it's going to drop. Okay, so that's ball, and what he's going to do is he's going to throw this up in the air. And it's going to come back down like that. We're going to pretend this is in all one dimension. I drew it a little bit differently so you can kind of see it because it's going to be at the same position twice when it's going upward and downward. So we'll just pretend this is all in one dimension. So the first thing I need to do is draw my coordinate system or my axis. So that's going to be my y-axis as y is up. For this type of problem and 2D motion. This would be y of t is what we're saying this is. So it tracks where it is along the y-axis as it moves in time, as a function of time. And we know what that is. That's an equation of motion that we have. This is too small. Okay. So we know what y of t is. It's y0. And I'm actually going to put that 0 on at the end. So y0, v0, I'll put that 0 on at the end. Plus a divided by 2, I'll put that 2 on at the end. T squared, put that 2 on the end. So it looks all normal. I know this may be a little awkward at first, but I'm going to fill this out with subscripts and superscripts, exponents, just so it looks more compact and it's not as confusing and follows a normal notation. Okay, so that's our equation of motion for position. And so projectile motion, we know we can look at it right off the bat and we can say, as long as there's no other forces, our only acceleration is going to be gravity, and that's going to be in a downward position. And so, let's see, I can make gravity blue. So make gravity blue, and that's going to be, we know that the acceleration A is going to equal A is going to equal negative G, because G equals that, which is negative 9.81 meters per second squared. And so we can replace this with G, and then we basically get the same thing, except we get a minus G. We know what that is, but I'm just going to put G in it, so we can always start off and know that we know gravity. I'm going to go through this whole thing again, but it's worth it to have these written down. Okay, so we're going to use that a lot, and what that tells us is, need my fraction there. Okay, so this is great. What this tells us is, because we know gravity, all we need to know is the initial position and the initial velocity, and we're going to know the position at any time t. This is g here. Okay, so all we need to know is initial position, initial velocity, and we can know the position at any time. We also know we can figure out the velocity at any time. That's another equation of motion that we have, which the velocity of t is going to equal v0, and I'll put the 0 on that, plus a t. And that's just going to be a times t. And here again, we know that's g, so we can rewrite that. Negative g times t. Okay, this also tells us that we will know the velocity at any point if we know t, given the initial velocity. So that's great. What we're going to do is we're going to choose some values for initial position, initial time. Okay, I'll do this position vector, or position point, and it can be a vector, but we're just going to call it distance right now. That's that distance there. We're going to call that 15 meters. That's going to be y0, 15 meters. Okay, and then actually I'll go ahead and put that up there where that actually is, which is right there. And then we'll have an initial velocity, and I'll do velocity in green, light green. So that's going to be our initial velocity, and we're going to say that is 10 meters per second. Right there. Okay, so right here you can see initially at time 0, this time 0, we have a initial position of 15 meters. We have initial velocity of 10 meters per second. And because we know that, we can say what the position, and we can also say what the velocity is at any time t. Because right here we have initial position. And so say we plug in 0, we can tell that this will go to 0, the second factor, and then the third part will go to 0 too. So we'll just have y of 0. So that's a trivial example. The same for velocity. If we put in t here, cancels that part out, and then we only have velocity. But we'll see what we can do is figure out what the height of this will be, where we'll stop. But what your book does, it just goes in increments of seconds, 1, 2, and 3 seconds. So that's actually what I'm going to do here. Okay, so we'll want to see where this is at 1 second. And actually, I'll draw the ball at the top here. So this is the ball as it reaches the top. Hopefully you can see that with the path, but I think you can. Right there. Okay, so we know this is going to have gravity still acting on it, because gravity is going to be a constant negative g, and that's going to be going down. But we know that the velocity, since it's going to be changing directions, is actually going to be 0, meaning it's going to be temporarily, instantaneously at rest when it's at the top. Then I'll just go ahead and draw the other parts of where this ball is, and the acceleration and velocity at those points. So for this point, we're going to have gravity again. Gravity again, when the ball reaches where we are there, it's going to have gravity going down, still at the same rate, except for our velocity. It's going to be going down, because as it goes down, that velocity is going to be acting on it, and it's going to continue to go down. So I'll say this is at some v here, and that's still negative g, so we know that. And then the last one is going to be when the ball hits the ground here. Okay, so that'll have a g going down too. And then the velocity, we'll make this a little bit, it's probably not going quite that much because it's about the same as when it's coming down. We can figure that out by logic. And then this velocity is going to be really big when it hits the ground. So we'll just go there. And so I'll actually make this one a little shorter, like that. Okay, so we're going to figure this out for t equals 1, this equation here. So y at 1 second, oh, I want that in blue. Okay, so y at 1 second we know y of 0 is 15 meters. We know the initial velocity is 10 meters per second. That's times 1. And we know the gravity we're going to estimate to be 10 meters per second squared, or negative 10 meters per second squared since it's pointed downwards. So negative 10 divided by 2. And so that's 5. And we know 10 times 1 is that. We know this is 5. And that's going to be multiplied by 1 squared, which is 1 times 5 is 1. So that's going to give us an initial height of 20 meters. And so you can go ahead and work that out for yourself if you'd like. I did it kind of fast there, but that means it's going to be at 20 meters. So we can also figure out what the velocity is going to be at 1 second. So I have the velocity here too. That's going to, initial velocity is 10 meters per second minus 5, or I'm sorry, minus 10 meters per second squared, which is down, times 1. We know that that equals 10. And so that's going to equal 0 meters per second at 1 second. This is 1 second. And what this tells us is the velocity is 0, so it's at rest. So this is 1 second here. We go ahead and write this as at 1 second. We know that because the velocity is at rest. And then this is going to be 20 meters is the height that it goes to. And so we could have calculated that another way, but by just putting the going by 1 second stuff, we figured it out. So I did that the quick way. Other problems won't be so easy, but this is the easy problem. Okay, so we can go on to 2 and see where it is at 2 seconds. Okay, so y of 2. I don't know why it keeps doing that. Okay, so same equation here. Initial position 15 meters, initial velocity 10 meters per second, so first times 2 there. So then it's 20. And then negative 5 times t squared, which is negative 5 times t squared is 4. So that's 20. So 20 minus 20 is 15. meters. Okay, so this is telling us at T2 it's at 15 meters. We started at T0 at 15 meters. Well, it tells us right here that this is where the ball is at 2 seconds. So this is a nice problem because it works out real easily. The math works out, but it gives you a good demonstration how all this math works. So we can figure out what the velocity is here at t equals 0, or at t equals 2 seconds. And it's going to be, I'm going to guess it's going to be 10 meters per second because it should be, since it's symmetric, it should be going down at the same speed that it went going up. But we'll verify that. So it's, our equation is going to be initial velocity of 10 meters per second. And then it's 10 meters per second squared is the gravity times 2. So that's actually 20. So it is actually different because it's negative 10, as you can see, meters per second going down. That's V2. Okay, so we really only have one more, which is at t equals 3 seconds. And so we could also figure out when to hit the ground and how much time that would take. But here we're just going to plug in 3 seconds anyway and see what we get. And I betcha we'll get the same one because that's just how the problem works out. So this is times 3 for t. So that's going to go to 30. That's plus, I'm sorry. Okay, so then it's negative 5 times 9, which is 45. Okay, so 45 minus 30 is 15. Negative 15 times 15 is 0 meters. So that's when it's going to be hit the ground at 3 seconds, and we can go ahead and label that right there. So this is a kind of a nice little problem. We can figure out the velocity when it hits the ground, which I think is one of the more interesting numbers in this problem, or things to find out in this problem. So again, we have 10 meters per second minus 10 times 3 per t. So that's going to equal 30. And so that's going to be negative 20 meters per second is the velocity at time 3. Okay, so that's a good example of projectile motion in 1 dimension, and I'll move on to 2 dimensions and vectors. Thanks.